spatially. You start to play with those relationships, and you start to see that this is a primary structure, and as it exists in one plane. And as it starts to move, now it exists in two planes. And then when you move it in space, then it exists in three planes. So this is a primary, then secondary, then tertiary structure. And in the same way, you have, spatially, you have this kind of syntax where, say this is the double helix, and as this starts to move, you have, you're going from the primary structure and secondary structure to a specific tertiary structure. And then when those tertiary structures interact with each other, there's a quaternary communication. To me, it's like, getting it. It's like getting a paragraph, getting the content of something is that transfer of that kind of communication. There's something very special and hard to describe about the way in which things come together and we kind of communicate. I started thinking about, well, what were the existing modeling systems? And that really came down to two basic modeling systems. One was stereotonic modeling, which is stacking, which is really about the development of agrarian life, civilization, sort of the classic way of looking at building, sort of like the brick. The Lego became that paradigm. And then after that, there was this new modeling system during the Industrial Revolution, and it was about mechanical engineering, so how to build girders and beams and bridges and skyscrapers. And that's called tectonic modeling. And the play system and modeling systems that are analogous with that were things like erector sets and Meccano. And then later, Buckminster Fuller developing these zones and geodesic domes. But they were all still based on tectonic modeling. And it wasn't until computer-assisted design did people start to look at tessellation and reverse kinematics. And so I started thinking about, well, how to integrate these kind of dynamic models and these emergent systems that I had been looking at through the behavior of these softwares that mimic organic behavior and learning and autonomous learning systems. And so I started designing a system that was based on the idea that life is really moving geometry, and that for me it was very hard to describe when I took my hands and I put them together like this. Is this one thing or two things? It's like, is this one thing or two things? Is this a different thing? And I started realizing, well, there wasn't a modeling system to describe that kind of interaction. And so I started realizing that the same thing was true with DNA, that DNA is a double helix. And we're told, okay, this is a double helix of DNA in school. And the question to me was, well, why, if this is in the same molecules in every cell of my body, why doesn't it always make the same thing? You have this tertiary structure, and it folds up in space into a different conformation, like a sculpture. And as a sculptor, I thought, okay, all these molecules, these proteins, have a very specific three-dimensional form. And the thing is that there's areas where they are not accessible and areas that are easily accessible. And so when they're read from the areas that are accessible. And so those are the things that are translated. So it's not as if you can read the whole DNA at once, just like you can't read a whole book at once. You end up reading what's exposed, so that the differences in tertiary and quaternary form is what creates the difference between what is translated and built. And so in each of our cells, we may have the same exact DNA, but it's the tertiary and quaternary forms of that make a difference, so that we're not just making one homogeneous protein. That's why we're differentiated. When you create something out of a building block, and you take it apart, it's kind of what we call its creation-destruction cycle. Once it's taken out of that primary form, it doesn't have any organizational principle. But the thing about ZOOB is that there's a secondary behavior, which is there's a self-similarity. So there's an organizing principle that allows you to restructure this form within the resonance of its geometry. And so here, I'm able to take apart the double helix and put it back together again. And so it has that level of self-similarity. The idea with the form of the ZOOB unit was that I made it to be like a prosthetic, kind of an extension of my own body, like my own fingers. And it's made so that it'll stand up on its own. So again, it has that idea of it being a figure, like a homunculus, like this miniature person. And the citroid, which is the head of the ZOOB unit, has 122 craters. And those craters correspond to all the Platonic and Archimedean geometries, all their faces, their vertices, their midpoints. And so what that means is that you have this flux between all the possible molecular, architectural angles that would create any kind of moving geometry and form. Then below this sphere, the citroid, is this neck. And the neck is there so that you can actually articulate the ZOOB unit and create a triangle and create a straight line and all the different geometries in between. So you go from a triangle to a square, to a pentagon, to a hexagon, to an octagon, to a straight line. So you have the neck, you have the citroid, and then there's the body of the ZOOB unit. And then below the body, there is the jaw. And the jaw has two petals, and those two petals are exactly half the surface area of a sphere, 2 pi steradians. And so a sphere is 4 pi, and when you put two ZOOB units together, you make what's called a full orbit connection. And so it's this rigid connection that goes back and forth. So here you have the petals, the full orbit connection, and then inside then you have this cone, and that cone is what articulates those different craters to create the different positions and geometry that you have with the ZOOB unit. So when you connect 3 ZOOB units together, you have an infinite range of motion within the center of this as an imaginary sphere. And if you can imagine that you're able to touch all the space on the circumference of that sphere, all the points within that sphere, and then close it off and create a closed system, a triangle. So the first closed system is the triangle. And here we have a triangle that's dynamic and can move. If you take this triangle, this isn't just a triangle. The triangle actually rotates on its axes. So all 3 of those joints are rotating. So when you connect 2 triangles together, then all of a sudden you end up with a type of movement that is, complex movement. This is the way that, suspension works in a car. And so you're moving in all these different planes at once. So you have a dynamic behavior. And so as you keep on adding different sub-assemblies, like triangle onto triangle, with just 3 triangles, you're able to show this behavior of 3 triangles, which is very similar to the way that our biomechanics work. This is the way our pelvis works. So it allows you to model dynamics with very simple relationships. Now this is a triangle in one plane, but as I can fold it and it'll start to create a corner of a cube. So once I have that corner of the cube, I can show the dynamics. I can take that cube and I can make it into, that square can turn into the plane